In this section, we're going to talk about circuit diagrams and the rules that go with it. So, circuit diagrams, these are all the possible symbols that you can have for circuit diagrams. Well, not all the possible symbols, most of the common symbols that you'll see. The ones that you should probably keep note of are the resistor, power supply, and yeah, you've probably already seen the rest of them. So, Kirchhoff's rules. So Kirchhoff's rules or laws have two parts to it. Number one, the sum of the currents flowing into a junction is equal in magnitude to the sum of the currents flowing out of that junction. So what goes in must come out. That's why the current going in must be equal to the current going out. Two, in any closed loop of a circuit, the sum of the voltage drop must equal the sum of the EMFs in that loop. So same thing, the amount of voltage you put in must be equal to the voltage that is used. So how does this work? Well, if you look at a point in the circuit, which is right in the center here, in the center point, the current going in must be equal to the current going out. So if we split it into the current going in, the current going in has 1 amp as well as 4 amps. That gives us 5 amps in total. The current going out, you have 2.5 amps and 1.3 amps. That gives us 3.8 amps in total. Now, because they have to be balanced, and there's more current going in than out, the current we're trying to find, which is I, must be equal to the, must be on the part where the current is going out. So, the current going in must be equal to the current going out. We have 5 amps on one side, then the other side is 3.8 amps, and you must add the last bit of current that is going out. So I must then be 5 minus 3.8 amps. That gives us 1.2 amps, and it's going out. Okay. Find the values of the currents A, B, C, D, and E, as well as F. So what goes in must come out. That means on this first part here, you have 15.3 going in, and you already have 7.9 milliamps coming out. The other part must make it added to 15.3. So for the first current, 15.3, that's going in. Then we have 7.9 coming out, plus the current of A. So then if we solve that, we will get 7.4 milliamps. For part B, because we know the total was 15.3 milliamps going in, you also must have 15.3 milliamps coming out. And then current C. Now, what do you have to do for this part? It hasn't split off here in this particular point yet. So that means C will have both of a current that goes through section D as well as the current D. So what I mean by that is this part and this part. So C must include both of those. So the current C must be based on the 15.3 milliamps going in. You already have 2.1 amps on the right hand side and current C added together. So current C must be 15.3 minus 2.1 amps. That gives us 13.2 milliamps. Current D. Current D is on the left. We have 13.2 going in on the left side here. Oh god. And then if you have a look on the top here, there's 6.5 milliamps going into that section D. So that means this must be 6.5 milliamps plus current D. So current D must be 13.2 minus 6.5 milliamps. That then gives us 6.7 milliamps. Current E is the last one. Oh, second last one, which is here. What goes in must come out. So current E is equal to 2.1 milliamps. Current F is on the top here. If you have 15.3 coming in at the start, then you must have 15.3 going out. So current F is equal to 15.3 milliamps. Alright, calculate the unknown voltage drop at BC in the figure shown on the right. So the total is 9 volts and we have 5.2 volts being used there. So that then gives us 3.8 volts.